Welcome back. Today we're going to talk about a kind of differential equation problem called an initial value problem. So we're going to define that term, initial value problem. We're going to check if a given function is a solution to an initial value problem. And then we're going to solve some initial value problems graphically using slope fields. So yesterday we mentioned that basically every differential equation has an infinite number of solutions. Even the simplest differential equations, the ones that you encountered in Calc 2, have this property. For example, if you have the differential equation y prime equals x squared plus 1, then the full collection of solutions consisted of all the functions of the form y equals 1/3 x cubed plus x plus c. And every possible value of c gave you a different solution. If c was 0, that gave you one solution, but c could just as easily be 1 or -1 or pi or square root of 7. Every real number c gave you a different solution, and so there were infinitely many solutions to this problem. We also saw this when we were sketching solutions on slope fields yesterday. Depending on where we threw our dot, depending on where we put our leaf into the water, we drew different solution curves using those tiny line segments. An initial value problem is just a way for someone to specify which one of those solutions you should be interested in that problem. An initial value problem is an ODE together with a point or points that a solution to the problem must pass through. Out of the infinite collection of possible solutions to this ODE, give me the one solution which has this special extra property, that it passes through this specified point or points. For example, let's solve the initial value problem, where we want the solution to the ODE y prime equals 3/2 x plus 4, the specific solution that satisfies y of 0 is equal to 3. Or in other words, we want the solution that passes through the point where x is 0, the input is 0, and the corresponding y value is 3. The first thing that we're going to do is we're going to solve the ODE. We're going to find all possible solutions to the ODE, and after that we'll figure out which one passes through the specified point given to us. So, using calculus 2 techniques, the solution would be the antiderivative 3/2 x squared plus 4x, and then plus some arbitrary unknown constant c. But now we're going to specify that we need the y value to be 3 when the x is equal to 0. So I'm going to go into this general form of a solution. I'm going to replace the x's with 0 and replace the y with 3, and from that figure out what c must be. The y is 3 when the x's are 0. And after simplification, that tells us that the c value has to be 3. So in conclusion, which of the infinitely many solutions is the one that we want in this initial value problem? We want the solution y equals 3/2 x squared plus 4x plus 3. There is now a single solution to this initial value problem. Now in problems like the one above, where the ODE contained only a first derivative, it's common to see information given only about the original function. y prime equals something, the ODE contains the first derivative, and our point contains information about the original function only. But in examples like this one at the top of the page, our ODE contains a second derivative, y double prime, and in ODEs which have a y double prime, you're more likely to see information not only about the original function, but also about the first derivative. So let's see if the function y equals 2 cos 3t plus sine 3t is a solution to the initial value problem given here. Now, in order for this function to be a solution to this initial value problem, a total of 3 conditions have to be satisfied. First, the function has to solve this ODE. Second, the original function has to equal 2 when the input is 0. And the first derivative has to output 5 when the input is 0. If all 3 conditions are satisfied, then the function is a solution to this initial value problem. Let's go ahead and let's find the first derivative. That's given by y prime. It's like -6 sine 3t plus 3 cos 3t, which would make the second derivative equal to -18 cos 3t minus 9 sine 3t. So now that we've gotten that information, let's check whether each of these equations is satisfied. If I check the first equation, is y double prime plus 9 times y equal to 0, y double prime we just found was -18 cos 3t minus 9 sine 3t plus 9 times the original function, which was 2 cos 3t plus sine 3t. Let's check if that is equal to 0. But if you distribute and simplify that, combine like terms, the plus 18 cos will cancel the minus 18 cos, the plus 9 sine will cancel the minus 9 sine, and so this will be 0 equals 0, and that's a true statement. So the first condition is met, so far so good. Let's determine whether or not the second condition is met. If I plug an input of 0 into the original function, will 2 be the result? So y of 0 would be equal to 2 times cosine of 3 times 0 plus sine of 3 times 0. Since sine outputs 0 and cosine outputs 1, this would be equal to 2 times 1, and that is 2. That's fine. However, if I look at the third condition, that if I take y prime and plug in 0 to that, the result should be 5. If I plug 0 into y prime, I get -6 sine 0 plus 3 cos 0, which simplifies to 3. That, unfortunately, is not equal to the 5 it's supposed to be, which means that the second condition is not satisfied, and since even one of these conditions is not satisfied, no, this y is not a solution to this initial value problem. It's a solution to the ODE, but it's not a solution to the entire problem. Let's mix it up a little bit. So this time they want us to find a value of k, so that y equals k times e to the 5t is a solution to the initial value problem y prime equals 5 times y, and y of 0 is equal to 300. So the first thing that needs to be true is that this function needs to satisfy the differential equation in this problem. So let's calculate y prime. The derivative of k times e to the 5t. By chain rule, that 5 comes down, and this is indeed 5 times what we originally had. Now, let's check and make sure that the second condition is satisfied. If I plug 0 into the original function, I get k e to the 5 times 0, which simplifies to k. And that is supposed to be equal to 300. So as a result of the second condition, we can conclude that in order for y to be a solution to this initial value problem, that the k value must be equal to 300. Y equals 300 e to the 5t is a solution to this initial value problem. Finally, let's review what it would mean to graph a solution to an initial value problem on a slope field. Below we have the slope field for y prime equals x over y. I have just gotten this from the Desmos slope field generator. And we want the specific solution that passes through the point where the input, the x value, is 1 and the output is 2. So what I'm going to do is I'm going to go into this Desmos graph. I'm going to find the location 1, 2. I'm going to drop a leaf at that location, and I'm going to see where the current takes us. So 1, 2 in this picture would be located right here. Now, there are one of two possibilities. The current is moving to the top right, or the current is moving to the bottom left. There are no directions on these line segments, so it could be either way. If the current is going to the top right, then following those tangent line segments, I'm going a little bit to the left and a little bit to the right, but the further I move, the more upward that I am going. So the leaf's path goes that way. On the other hand, if the current is moving in the opposite direction and I am being moved slightly to the bottom left, then the current will take me to the bottom left, then the tangent lines are becoming horizontal, and then they're pulling up slightly. So the curve looks a little bit like this, roughly speaking, hyperbolic it looks like. So that concludes today's material. Tomorrow we're going to get started actually solving some differential equations. But what we've talked about over the past couple of days represents some fundamental ideas that I don't want you to forget as you are going through the nitty-gritty of how to solve all these different types of differential equations. What is a solution to a differential equation? It's a function which makes the equation true. What does it mean to solve a differential equation? It means to find or describe all possible solutions to that diffie-q. What's an initial value problem? An initial value problem is a differential equation together with a few additional pieces of data that are used to take that infinite collection of solutions and reduce it to maybe one or two specific solutions which meet your additional criteria.